very stable, about 96.8 to 98%. So the optimization are not always good for accuracy. They help PyTorch a lot of, and they cost TensorFlow a little. That is the first half of our trade-off. And know the speed side where the picture is much very more positive across the board. Every single optimized pipeline beats its own baseline on all three GPUs, no exceptions. TensorFlow reached the high test speed over 3,000 images per second on the GH200 and about a 289% improvement on the L4CS. PyTorch also gains a lot of about 250% on the GH200. Money against are smaller, but they are speedy, and Monai actually leads on the RTX 4090. So even though optimization costs TensorFlow same accuracy on low speed, it is the clear winner. This is exactly the trade-off in the title. So trend time is the other side of the coin, and it tells the same history impact time. PyTorch is the slowest setup everywhere, but once we add daily NT and Torch compile, we cut the training time by up to about 70% on the GH200, a very big drop. TensorFlow OPT because the time they be about 50 to 52% on the GH200 and L4DS, but increased only about 50% on the RTX 4090. So the benefit depends on the hardware. And the Monet OPT is the fastest absolute timing of all on the RTX 4090, about 2,200 seconds. So the best framework really, but depends on the which GPU you have in front of you. And memory, this is often what decides if you can train and throw a small card. Three clear profiles. One is the most stable and the most memory friendly. It stay RW6 on 87.4 gigabytes, no matter the GPU or the optimization. PyTorch was the design high test memory use about 18.7 to 19 gigabytes, and its optimized version doesn't shrink much. TensorFlow shows the biggest drop after optimization. It goes from about 12 gigabytes down to a little as on zero point 0.7 gigabytes on the GH200. So if memory is hard limit, Money is the safe, predictive choice and optimized version. TensorFlow can be very another question, which optimization is really doing the work. So you run ablation turning on one technical time. The answer is clear. FP60 max precision is the main source of the setup on its own. It wants the trend time from about 3,000 page 265 seconds to 2,254 seconds, and it almost doubled the throughput from about 672 to 1,328 images per second with only a small drop in AUC. Daily cosine and IMA each have a small effect on their own, but the important result is the bottom row. The full stack keeps the accuracy almost perfect. AUC goes from 0.9858 to 0.9854, almost the same, while giving most the speed gain. So so we get the speed without paying for in quality. Let me bring this together. First, AUC can more with the software than with the GPU. The framework and is optimization shape quality, while throughput and time depend on both the framework and the hardware. Second, there is no single winner. It is a trade-off. Control optic gives the highest throughput on the G8200 and L4DS. The torch optic gives the best balance, 98.5%. AUC on all three GPUs. Monai gives smaller but more stable, predictable behavior accuracy platform. And across our pipeline, we saw throughput improved by up to 289% and runtime dropped by up to 70%. Without losing accuracy, the critical message is this. Powerful optimization makes diabetic retinopathy training really possible in all resource settings. Looking ahead, we want to expand this to larger datasets, multi-GPU setups, and other medical images tasks. Acknowledgements. This work was supported by Petrobras, NTT, and CAPES under Finis Code 001. Our experiment reached 5,000 testbed supported by BIA, Guinea, and Air East, Canada, and Spartan. And on the trade infrastructure at our institute. And thank you to all of them. For question, send me email, please. This is it.
Okay, thank you for your presentation. Are there any questions? Okay, we have no question. Thank you again. So the next paper is automating the technical validation of FHIR implementation guides, a data-oriented framework within the HFPT project. Okay. And the speaker is Leopoldo Silva.
Yep. Thank you for the introduction.
We need to. Can I share the screen?
Sure.
Okay, thank you.
Maybe start.
Okay.
Start the presentation.
Yeah.
It is ready.
Yes. The floor is yours.
Okay, thank you and good evening, everyone. So I am here to present our work and paper that we name Automating the Technical Validation of FHIR Implementation Guides. Then in our institute, I am from the CCG ZigDV Institute. We are an RTO based in Guimarães, so nearby, on the Minho campus, but not the Volta campus, but the Azerrain campus. This work is made under the Health for Portugal agenda. It is financed or funded by the RPP. I don't know how to say it in English. Sorry. Anyway, in Portugal, there is this strategy for interoperability among healthcare software. So there is this will to make our technical ecosystems and then application ecosystems talk to each other. And under this strategy, there is this agenda where this project is located, and we are in a particular project, the A4.4.3, that develops FHIR specifications for several use cases for the healthcare. In our activity that led to this work, our goal was to do the technical validation of these FHIR implementation guides that were being done. So what is FHIR? FHIR is an AL7 standard that is sought to allow for the exchange of healthcare information in an interoperable way, syntactical compatible, semantic compatible. So it is not an easy standard. It has a hierarchical form that for us, that we are not from the medical area, it is not easy to understand. We understand what is XML and the schemas, we understand all of that, but the semantic and the syntactic that these standards have are not easy. And so they follow this hierarchy where we have the core resources, and every country has their own core resources. In Portugal, we have the Portuguese core resources. And then in each resources, we have the profiles and the extensions. And over here, we are trying to delimitate the main core profiles to special use cases. Then we have the terminologies and coding systems. Over here, we are talking about semantics. When a medical practitioner do a consultation and want to state that with this patient, I did this consultation, there is a code system, actually several code systems. It is one of the challenges we face. And then finally, we have the implementation guidelines that aggregates all these profiles and try to make them compatible with the Portuguese rules or the international rules that apply to each country. So it is always this hierarchy starts from the broader spectrum, and it tries always to get more a small view of what we are trying to transmit in these messages. So anyway, in this work, so we are in this project, and many of our partners are doing implementation guides, building implementation guides, FHIR implementation guides for Portuguese use cases. And the question is always, are they well done? So the people that are doing these FHIR implementation guides are not every time technical people. So they don't understand the schemas and what is XML, what is JSON, what are we doing. So we intervene here. We are the technical partners, if you wish. And so this is a question. Several implementation guides were done, and in our activity, we are trying to figure if they are well done. And we have half a dozen implementation guides, and each implementation guide have on itself some dozen messages, example messages. And then the software houses that are doing software that will use these implementation guides are giving us hundreds or even thousands of example messages. And the question is, are we all as a group doing a good work And when we start doing this verification, we did use an application that is from Age L7. It is the validator. It is a Java command line application, if you wish. And we have one of the authors doing these manual verifications and looking at XML reports that were hundreds or thousands of lines in length, and was trying to figure what is wrong with these profiles and with these messages, what is missing, what is the quality of what is being produced. And this work was taking hours for him to do. And so we decided to implement, to automate what he was doing manually in a relatively, sorry, I was looking at the wrong slide. So in a relatively simple architecture to start with, where we have a set of messages. Again, if we look at the profiles, it is on the dozens of messages. But if we look at the application message sets, we are talking about hundreds or thousands of messages. And so we did a matrix to automate this work. So we have this Java validator, this tool that we are using. And so we built a small application that is able to orchestrate and test all these messages in sequence and then aggregate the results to ease our work and our job of validating the implementation guides that our partners from the health sector were doing, and the application messages that the software houses were doing. So we started by producing a normalization of the messages of these results from the validation. Again, we are talking about big reports in XML, so it is good information from a machine to machine point of view, but not for humans to consume, and much less to give our partners the right indications about what should be done to the work being produced. So we started by simplifying the XML and flattening the data structure, if you wish, and obtain the data sets about what were the errors, where they were happening, in which file version, in which implementation guide and message. So we did these data sets, build the data sets, always with traceability in mind. So I want to know if I detect an error in a consultation message, what was the process this message was included in, and applied this to two domains. So the project itself is building half a dozen FHIR implementation guides, but we choose two to develop this work. One is a more vertical implementation guide because it is related to respiratory issues and consultations, and so we have observations, resources, and data sets. What the doctor saw, and these type of registries, to the condition, to what was the interaction with the patient. And so we had this vertical implementation guide, but we also had an horizontal implementation guide that was related to the admission process. So when a patient reaches the hospital, it has to identify himself, so a process will be open to him. A large number of identifications will be generated, and these identifications will follow the patient all over his medical process and will be included in the other implementation guides, in particular on the respiratory one. And so we were trying to validate that all these business processes were possible to implement and were being well implemented. So one thing that we noticed at first, so the first implementation guides were done to FHIR version 3, was that there was a large number of errors, syntactical errors. So the messages, the application messages that we were seeing did not validate in the AL7 validator, so they have syntactical errors on it. And so we started to interact with the software houses to make sure these syntactical errors were corrected. And in later versions of the implementation guides and the implementation message, the application message themselves, we saw a large reduction in the errors. And in particular, in the in the workflow IG, the one from the admission, we ended in a situation where we had no errors at all, at least in the messages we validated. And so we believe that this process we develop and this automation help the project to make the implementation guides mature. The same did not happen in the vertical one, in the respiratory issues implementation guide. However, something that was curious or is curious to note in this research is that even if the errors disappear, another type of warnings came up, in particular in the implementation guides that had 0 errors. Now we start to detect semantic problems. In FHIR, they call this the warning. So it is something that it is possible to process. However, the semantic is not well done. So they were using different code systems, different taxonomies. And so this seems obvious for we can't really detect the semantically errors if there are syntax errors. However, for our partners, again, they are not in the IT sector, this was very valuable and allowed us to mature these implementation guides and applications that are using them. Finally, and this is something we are still working, the validator detects these syntax and semantic errors, but don't give non-technical way to fix it. So now we are trying to make human readable recommendations for all the stakeholders in the process. So from the authors of the implementation guides, we are talking sometimes, in particular in these examples I have there. Yeah, I have there. Sometimes it is stuff like we are using underscores where we should use an hyphen. And this is something, this error comes from the authors of the implementation guide. Or we are using an invalid language code, and this is part of or a fault introduced by the software vendors. Again, what is there may seem obvious to a technical person. That is the language code is not well written, or does not follow the standard. And finally, we are also looking at or giving recommendations to the project governance that sometimes the validation is in the code system itself. And this is very prevalent, at least in our application ecosystem, where we do have practitioners that work in several places and are used to a code system. And so when I do a consultation to a patient, I am used to use a code system, and this is a numerical number I introduce in the system. And so when I change places, the other place uses another application that uses another code system. And so in the end, I end with a registry that is semantically incorrect. And so we are also trying to find these points of failures. Yep, I'm there. So finally, in conclusion, we do believe that this project and our activity helped the consortium to reach a level of quality that it will not without our work and automation we did in this process. Just a notice that I might have forgotten in the beginning. When we start doing this, per message, it will take us half an hour, 1 hour per message. So we took a message and applied the validator, and then to transmit the results to our fellows. This process was very time consuming, and in the end, after the solution was done, we are able to apply this to hundreds of messages and aggregate the results, identify the most common problems, and so lower the maturity of the implementation guides. And so these are the two first points that are there. And finally, we are now trying to, and this is the future work, if you wish, even if we are doing it already, we are applying it to all the other implementation guides done in the project, and we intend to build a service on this. Not us directly, but our project partners. So this can be integrated in automated validating and possibly certification paths that will help to mature all our health ecosystem. And this is it. I am Leopoldo Silva, a senior researcher from CCG. You are welcome to visit us in Guimarães in the Minho Campus University. Thank you.
Okay, thank you so much for the speech. Are there any questions?
Just a comment that your work is very important.
And it is not easy as well, because we are not medical practitioners. So we are always exploring new fields and leaving our comfort zone. And this is one of those examples. Yes, but we do believe that we have done a valuable work. Thank you.
Thank you. Okay, we have one more paper. That is dynamic regression algorithm and multi-objective query optimization in Spark SQL. And the speaker is Dr. Trang Dan Lee. Is here? Is virtual? Let me check.
On the room. Hello, can you hear me? I think that your microphone is muted. Can you please check? No, we cannot hear you. It seems that you are muted. So can you please try to change your browser? For instance, if you are using Chrome, try to use Firefox. or if you are using Firefox, try to use Chrome. First of all, can you hear me? Okay.
Yes, I can hear you.
Okay, excellent. Okay, so you can start your presentation.
Okay. Good afternoon. Uh, I will share my screen.
Yes, please. You can share with the third button on the toolbar at the bottom. Okay,
Yeah.
excellent. Excellent.
Good afternoon, everyone. My name is Sing Dũng Lê from Thủy Lợi University in Hà Nội, Vietnam. Today I will talk to you about dynamic regression algorithm and maintain quantitative query optimization in Spark SQL. Okay. For the first, the motivation. We know that cloud computing follow as a pay-as-you-go model. So query optimization should balance these two conflicts of pieces like execution time, monetary cost, and in the cloud computation computing Spark SQL Catalyst optimizer is effective for trigger predictive optimization, especially during reordering. However, in many maintain objective query optimization problem, they keep only one and supplant. So is may discuss this trade-off then. Two key challenges is that accurate cost estimation in a dynamic cloud environment. And another key challenges is efficient searching in a very large Pareto solution space. So in this paper, I would like to integrate Dream for dynamic cost estimation and NSAS for efficient Pareto search in Spark SQL. For the existing Spark SQL, they use CBO and dynamic computing to join ordering. They optimize mainly Scala cost. So it's not suitable for the two MOQP. The remain is used that traditional machine learning cost model often need to have a large training data. And another is used that NSA2 and NSA3 still have a high selection bias in the final front. So in this paper, I would like to give a brief determination that mm, been validated in Spark SQL. So the contribution of this paper that we validate an integrated Spark SQL extension with combining Stream for library dynamic estimation and SJS for adaptive quick-based Pareto search. With the background in the previous work, we propose a dream dynamic regression algorithm with, for the cost estimation in environment variability. So the finish, the full code execution is writing as the first question, and the dream evaluate the model quality using the coefficient of determination with the second question. instead of always using all the historical data. Dream will select a sufficiently accurate model with a low computational cost. This is especially useful in Spark as well, where workload and runtime conditions may change dynamically. With NSGA and NSGS, NSGA is the class of non-dominated sorting semantic algorithm are widely used for solving multi-objective optimization problems. With NSGA2 use a crowding distance to maintain diversity on the Pareto front, and NSGA3 use a reference point, which is effective for many objective problems. Both algorithms share a relative low non-dominated sorting complexity, but their last front selections quite considerable for computation. So this multi-iteration of NSGS will replace expensive last front selection by grid partition and with the front grouping very simple. NSGS is designed to preserve convergence and diversity while reducing computation in the uh, selection phase. With current Spark SQL behavior, the catalyst may keep only the single best plan for each subset of the relation during join reordering. For example, with the table A, B, and C, we can have many ways to join, but the final retain only one plan. In MOQP, this printing make skip plan that are worse in one metric but better in none. So we would like to retain multiple logical plans and compare them under multiple objectives. This is architecture of our intention that when we integrate them in Spark SQL, query will be generated in multiple objective logical plans. After that, we use the model of integrate some model to input to the Spark SQL and choose the best query plan. The extension will input the logical optimization state of the catalyst. So it first generate a Pareto set of logical plans, and then select one's best plan based on user preference. With the Dream dynamic regression algorithm, Dream will use a multiple line regression model for the cost estimation. The key idea is that we update historical data more frequently than distant history. So the more data do not always mean it's the best practical model. The Dream select a model that's balance prediction accuracy, the limit historical data and computational efficiency. With the NSGS, the main idea is that NSGS is based on the non-dominated sorting like NSJ2 and 3. And the main novelty is the selection of the last front. We use a grid partitional and a simple front. Instead of using the crowding distance and reference point, the NSJS group solution in many grid cell. And after that, we select the best cell or the worst cell. the best solution of the Boltzmann solution in only one cell. If the last from remove k solution and objective space, the number of the bit statement is like n equal to k uh, like in the first equation. This allow that in automatic read determination. The benefits of this is future server diversity, reduce the global pairwise comparison, and the scale better in the group setting. The select complexity, the paper will report the selection phase complexity of NCAS as power of n multiplied m, which is lower than the 2 and 3 selection mechanism. In this table, you can see that the selection complexity of NCAS smaller than 2 and 3. The automated sorting remain with the O of n square, showing with the NSE family. The gain come from from the selection state. It is important because the planning latency in SQL remain low. So with the searching of the SQL with the evolutionary image, we use DTLZ as problem. The objective dimension is 4, 6, 8, 10, and 11, 12. In many algorithms, compare with NSA2, 3, and OVID, and configuration includes population size is n equal to 500. Maximum evaluation is 5,000, and we use the average of 50 independent runs. The metric when we would like to compare the quality of each of this algorithm, we use GP, IC, and FP. The lower is better. The lower value in comparison, the lower value is better for all three metrics. In in the first in the first instance, we can see that NSAS outperform competitor in most of the case for the conversion diversity and Pareto front approximation quality. For example, with NSA1, DTLZ1 with M equal to 6, NSAS value is only 7.09, and 10 plus minus 1, and with DT Z1 M equal to 8, and SCAS the value of MPFE equal only to 10 multiple with 1 voice. For the detail of the comparison, the generational distance and average compute times, we can see that in DTLZ1 3 M equal to 4, 6, 8, 10, 12. Many case situation NSAS have the best value quality, and the time computation times and the the time is very small when compared to the other algorithm. With quality in comparison of quality in both generation distance and average compute time, the result is the same. But NSJS have many good quality in many cases. With comparison of quality in maximum Pareto quantile and average computers, the result is the same with DT, LZ1 and 3, and number of objective is 4, 6, 8, 10, and 12. The value is very small. And with the average running chain, you can see that NSDIS estimate consistently faster than quality and usually faster than NSGA3. Stay competitive with NSGA2 while giving better solution quality. Uh, After that, with the experiment, we integrate um, two extension of the NSGAS and Dream to Spark as well with the step of Fourier processing and the step of generating new logical plans that with the level 0 we generate the possibility sub logical plan with and estimate the cost by Dream, and after that we choose the relevant logical plan. Um, and at the final, we have the Pareto plan set. Maybe after this, we move into the Spark as well. With the integration into the Spark as well, the extension will is implemented in Java by extending as well as Catalyst library. Instead of keeping only one logical subset, the the optimizer retains a set of intermediate logical plans. Dream predict multiple costs from historical study. NSGAS filter the candidate space and preserve the balance Pareto set. Finally, with the preference model, select one plan for physical planning and execution. The system level significant Pareto plays logical planning become particularly feasible inside Catalyst. With evaluation with Dream and NSGS is as well. We use TCP DS with the benchmark of TCP DS dataset with size is 1 GB. I know that it's very small, but it's usable for the test. The complex queries might conjoin. The average observed execution time is nearly to 40 milliseconds. Average estimation time execution is nearly to 39 seconds. Accuracy result that is we has estimation error smaller than 20% and approximate that 2.3%. And the integration achieves both practical optimization and high iterative precision. With the conclusion, we proposed multiple network optimization extension for Spark SQL. With the approach integrate clean algorithm and SCAS algorithm. With the experiment the results showing that we have a better conversion and diversity than NSE 2, 3, and MOE with lower or competitive runtime and with a practical utility inside Spark SQL Catalyst. With the future, we will validate the framework on the larger workload and test with the commercial cloud provider. And next, we plan to deploy the data management system and investigate the richer user preference model beyond with stock model. Thank you for your listening. Now we can discuss about, with our paper.
Okay. Thank you. Thank you.
Thank you very much.
Are there any questions? Okay. The session is over. Thank you for coming, and see you in ICCSA on the next sessions. Okay. Thank you.
Thank you.